Hello everyone. In this session we are going to discuss about stabilization technique. It is also known as biasing techniques. So here we can see today's topic is biasing techniques. We can see biasing, that means basically we have to apply DC supply in this circuit diagram, then it becomes biasing. So here we can see biasing of transistors. Biasing, or we can say stabilization, is a process of stabilizing the position of Q point. Q point is also denoted as quiescent point. So we need to design a biasing circuit which will keep the position of Q point stable on the DC load line. As we discussed earlier, DC load line, it is the line between the x-axis and y-axis parameters, which is VCE and IC. On this DC load line, we can put Q point at the bottom side or above or center point of this DC load line. Here we can see stabilization factor. Few factors are available. We can see here S is equal to delta IC upon delta ICO, where constant VBE and beta DC. These are the few parameters like delta IC, delta ICO, VBE and beta DC. First, we have to stable this value, then and then we will get stable Q point. Here we can see S dash is equal to delta IC upon delta VBE with constant ICO and beta DC. Third, S double dash is equal to delta IC upon delta beta DC with constant VBE and ICO. Here we can see. So this is the stabilization factor. Here we can see this is the stabilization techniques, in which we are going to discuss about these four stabilization technique. But here number 1 and 2 is slight modified techniques. So in this session we are going to discuss about basically 3 stabilization techniques. Number 1, fixed bias circuit. Number 2, collector to base bias circuit. And number 3, voltage divider bias. So among these 4, voltage divider bias is the latest and most useful technique among all stabilization technique. So let us discuss first fixed bias circuit. Here we can see this is the circuit diagram of fixed bias circuit, in which bias terminal is connected with the collector side. Here we can see this 4 stabilization technique. We have to solve mathematical expressions, right? So first here we can see fixed bias circuit. So in this theory we have to solve these 3 steps. Step number 1, find expression for the IB, that is your input side. Number 2, find expression of the IC, that is your output side. And number 3, VCE. So basically we have to find or define these 3 equations, or we can say expressions. So here we can see we are going to start with expression for base current, which is known as IB. So here we can see, so this is the circuit diagram for IB. So we have to select only base terminal, right? So current is flowing from plus to minus side. So we have to apply KVL, that means Kirchhoff's voltage law. So VCC minus IBRB minus VBE is equal to 0. Now take IB as a constant or subject. IB is equal to, it becomes VCC minus VBE upon RB. Now here VBE, actually for silicon it is 0.7 voltage, or for germanium it is 0.3 voltage. So comparatively VBE is smaller than VCC, because VCC value is in 5 volt, 10 volt and so on, whereas VBE is equal to 0.7 voltage. That's why here we can see VBE is less than VCC. So we have to neglect this value and it becomes IB is equal to VCC upon RB. So that is your expression for the IB, base current. Next, here we can see this is the expression for the collector current, which is known as IC. Now we have discussed about it earlier. IC is equal to beta DC IB, right? So just we have to put IBQ's value in this equation and we will find and we will get ICQ is equal to beta DC into IBQ, whereas IBQ is equal to VCC upon RB. Here we can see this is expression number 3, or we can say step number 3, expression for VCEQ. VCEQ we can find at the output side. Here we can see in circuit diagram, we have to just apply KVL at the output side. Now apply KVL at the output side, it will become VCC minus ICRC minus VCEQ is equal to 0. Here Q means quiescent point. If you are defining quiescent point or stabilization, here we can see VCEQ becomes subject is equal to VCC minus ICQ into RC. So this is your final expression for the VCEQ. Now here we can see collector to base bias circuit, and this is the circuit diagram for collector to base bias. Slightly change compared to the first one. Your RB, here we can see RB is in first technique, RB is connected directly with VCC, but here in this case RB is connected after RC, right? So this is the change in collector to base bias circuit. Now same we have to follow that techniques. Step number 1, expression for the base current. Step number 2, expression for the collector current. And step number 3, expression for the VCEQ, right? So in this circuit diagram, we have to just apply KVL at the input side. Here we can see VCC minus IC plus IB into RC minus IB RB minus VBE is equal to 0. Now VCC is taking as a subject is equal to RB plus RC into IB plus ICRC plus VBE. But here IC is equal to beta DC IB. So we have to just put this value in this equation. So we will get VCC is equal to RB plus RC into IB plus beta DC IB RC plus VBE. VCC is equal to RB, RC and beta DC RC is connected with the IB. So IB take a common and it becomes RB plus RC plus beta DC RC IB plus VBE. Now in this expression we have to find IB's value. So IB take a subject. IBQ is equal to VCC minus VBE upon RB plus 1 plus beta DC into RC. So this is your final expression for the base current, which is actually your input current. Now here we can see expression for the ICQ. We have to just put IBQ's value in this equation. Then you will find IC value. Now step number 3, expression for the VCEQ. Here we can see we have to just apply KVL at the output side, right? So VCC is equal to IC plus IB into RC plus VCEQ. Now we have to find expression for the VCEQ. VCEQ take as a subject is equal to VCC minus in bracket IC plus IB into RC. So this is your final expression for the VCEQ. Now last, this is the most important among this stabilization technique, which is known as voltage divider bias. Why it is known as voltage divider bias? Here we can see parallel resistors. Due to this, it is known as voltage divider bias. right? So first we have to connect one battery in terms of Thevenin's voltage. So here we can see this is Thevenin's equivalent circuit. Why it becomes like this? Here we can see there are two resistance R1 and R2, right? So it is actually parallel and it becomes RB. So we can write down RB is equal to R1 parallel R2 because both are available at the base side, right? So R1 R2 upon R1 plus R2 is equal to RB. Here we can see instead of R1 and R2 we can write RB only. So RB is equal to R1 parallel R2. And for these changes we have to apply Thevenin's theorem. That's why here we can see VTH. VTH, that means it is Thevenin's voltage, right? So this is your final and main circuit diagram for voltage divider bias, right? We have to just change base terminal. Instead of R1 and R2 we have to put RB, one resistance which is known as base resistance, right? And one battery connection which is known as Thevenin's voltage. Now step number 2, this is obtained for IBQ, where we can find IBQ at the input side. So we have to just apply KVL at the input side. Here we can see we have to start from VTH. So it becomes VTH minus IBRB minus VBE minus IERE is equal to 0. VTH minus IBRB minus VBE minus, instead of IE you can write 1 plus beta DC IB, right? So here we can see in place of IE we can write 1 plus beta DC IB into RE is equal to 0. Now we have to find expression of IB. So take IB as a subject. So IB is equal to, your final equation will be VTH minus VBE upon RB plus in bracket 1 plus beta DC into RE. Now step number 3 is easy because we have to find ICQ, and for ICQ we have to apply this equation IC is equal to beta DC into IB. We have to just put IB's value in this equation and we will get expression of ICQ. And last, step number 4, this is expression for the VCEQ. So for that we have to apply Kirchhoff's voltage law at the output side. For that VCC is equal to ICRC plus VCE plus IERE. VCE is equal to, it becomes VCC minus ICRC minus IERE. That will be your final expression for the VCEQ. And if we will define these 3 parameters, then and then we will stabilize the Q point. So that's why we are using this techniques in amplifier, because due to this technique we will get perfect output from the input side. Otherwise you will get distorted output at your output side. So that's all for today's lecture. Keep reading, keep learning. See you soon in next coming lecture. Thank you.